Linda, our topic today is the Transformer. Aside from a TV series and a movie, I don't imagine you've heard much about the Transformer, right?
Not that or electricity, perhaps.
Oh, yeah. Yeah, exactly. But let's get into what it does. And let's start from just the most intuitive sense of it. You know that words can have multiple meanings, right?
In the English language, absolutely.
Yeah, do you have any favorite examples?
I'm trying to think of a noun. Can you think of a noun that sounds the same? Could be a noun in one situation.
What about bird?
What are the multiple meanings?
Well, there's bird, the animal. There's bird like a 1950s cool guy, right? Wasn't that an expression like, hey, bird?
Oh, I never heard of that.
Or maybe it was like something that men called women, in which case we probably shouldn't do that.
Yeah, let's think of another word.
Yeah, okay, let's see. And then there's bird. A bird is the word.
Yeah, but I think that still means bird.
All right, so, well, actually, I don't know what that guy meant. Let's go then with the standard example you read in every paper and textbook, the word bank.
Okay, let's use bank.
Yeah, what's a bank to you?
Bank could be where, they keep track of your money and they loan you money, stuff like that. Or it could be like you're banking on something. Like you're kind of almost like, I don't even know what that really means. Is it like you're waiting or saving up for something? Kind of like betting on it?
The context you're referring to, I think it's that you have sort of wagered your assets on something.
Okay, I'll take that.
The more maybe traditional definition people would go for second would be bank of water.
Oh, you mean like a riverbank?
A riverbank, good example, yeah. So same word, the computer scientist in me wants to call that a collision, where two different meanings ended up with this mapping to the same word in English because a flaw in the design of the English language, I guess.
A flaw? I mean, I don't know. Does that really interfere with the way we communicate? I don't think so.
Okay, all right. I'm not going to ask you to give me that one, but definitely a collision. So you and I will, if we hear the word bank, we have to disambiguate which meaning it is, right?
Well, mainly it's about context.
Yes, exactly. But specifically, what is your process? What are the steps you do when hearing a sentence to make you decide which word bank it is?
What are the steps? Well, first I try and understand what the sentence is saying. I mean, we could say, let's just make up a sentence. Mm-hmm. Hey, I'm going to the bank to get $20. Mm-hmm. So you're probably not going to the riverbank.
What if you're a street performer and you're going to go down there and entertain?
I don't know if people really perform on the river nowadays. So you probably have to understand whoever's talking.
Fair enough. This is a process. You're right. You would do it from the context and from the meaning. What I was pushing you towards, and I don't know that I could have even gotten you here, was to think about like the very like rote meticulous steps that a computer might take. If we were just like starting out trying any idea and we wanted to disambiguate, maybe you would search for, does the word money appear in this sentence? And if so, it's probably the institutional bank. Or does the word water appear in the sentence? If so, it's probably riverbank.
Appears in the sentence?
Yeah.
Or where are you searching for? It appears in paragraph before or after?
In the exact same sentence.
Well, then you could just shorten the sentence and say, I'm going to the bank. So is that really a good rule?
What's your intuition on how accurate such an algorithm would be?
What's my guess of how accurate it'd be?
Yeah.
Probably like 50%.
Yeah, maybe something like that. Just for reference, how accurate do you think a human being would be in figuring out which sense it is?
Well, if they're a fluent English speaker, then probably at least 90%.
Yeah, if not higher. How could we work on our computer program, make it better? Well, we could start including other words besides water. Like, what if fish is there? And fish is probably the riverbank, whereas checking account would be something for a bank. And you could keep building up these lists. And then maybe you'd get clever and you would like say, well, let's get a bunch of chemistry terms that describe things about water. And suddenly you put the word solvent in as on the side of being the riverbank. But of course, the word insolvent also has an interesting meaning in the financial bank context. So that's not perfect either. If you try and just kind of stuff in the sort of keyword matching thing, maybe you could get it from 50% up to, 70% or 75%. But that's just never going to get you 100% of the way there. Do you see why not?
No, I mean, it makes sense. There's just situations we don't know about.
But on the flip side, you and I are doing it just fine in the high 90s. There's no explicit reason why a computer couldn't do it. It just has to do it maybe the way we do it or in some other clever way. But this keyword lookup thing isn't going to work, is my only argument so far. Does that make sense?
Okay, yeah, that makes sense. I agree.
The transformer is one of the tools we would use to crack a problem like this. And it's an attention mechanism, kind of like we talked about last time, even though I'm not real happy with my side of the conversation in our episode on attention. I feel like I didn't hit enough points, like talking about the attention distribution and stuff like that. But machine learning can read kind of the way we read, which is one word at a time. And as you get to a word, you're kind of in your brain have some of the context floating around. So it's through a process that's similar to word2vec that we've talked about before. Word2vec being the algorithm that you give it a word and it makes a numeric representation of the word. Even though you can't interpret that number, it's just some random numbers to you. It has all these special properties, like similar words have similar numbers.
What's an example, I guess? I'm not really sure what you mean until you give me an example.
Picture like an XY coordinate. We're going to draw a graph.
Yeah, that's just a standard chart. So yep. XY axis.
And now let's say we're going to convert the word bird into a numeric representation that has two dimensions, x and y. And it goes to x equals 2, y equals 2. So put a dot in your mental graph at 2, 2. You with me?
Yes.
Let's convert another word. This time let's convert the word parrot. Again, I'm going to tell you what the vector is, and I'm just making these up. The vector for parrot is x equal 2.1, y equal 2.1. Can you picture that?
Yeah, so why did it move both on the x and y? Why wouldn't it just move on the x or just move on the y?
That can happen in certain situations. The numbers themselves, there's no real meaning per se to what those numbers are. That's why they're not directly human interpretable, except that the algorithm is designed to map similar things to similar places. So let's do one more word, remembering now that bird and parrot are real close, right around 2, 2. Let's say we encode the word bicycle. And bicycle turns out to be x equals -5, y equals 15. Can you picture that?
Okay, 5 and 15.
So you can picture how that's pretty far from bird and parrot, right?
Yeah, sure.
So that's the idea of an embedding in general. It's find a magical algorithm, and we're going to kind of skip how you get it until we talk a little bit about the transformer here, but find an algorithm that converts words into numbers that have nice properties, like things that are similar are close together, things that are not similar are far apart.
Yes, so there's this weird matrix, and it just makes up whether they're similar or not.
Yeah, exactly. Thanks to this week's sponsor, the Great Courses Plus. For so many of us, and this really does apply to data skeptic listeners, I think, school is about cultivating the skills we'd use most in our careers. But there's so much more to be gained from learning skills that can also enhance our daily lives. That's why I want you to check out effective communication skills at the Great Courses Plus. Sure, maybe you're technically brilliant, but if you can't communicate your results, not just to your teammates and your boss, but to all the decision makers in your organization, if you've got any doubts about your ability to do that, it's an area to brush up on, and a great place to start is with the Effective Communication Skills course. If you enjoy that, there are hundreds of other lectures to look at. Make the Great Courses Plus your go-to for lifelong learning. And right now, they're offering Data Skeptic listeners a free trial of unlimited access to their entire library. thegreatcoursesplus.com/data. Once more, your free trial can begin today at thegreatcoursesplus.com/data.
So how do they determine whether a word's similar or not?
Well, that is the embedding algorithm you use. Now, we've talked about word2vec before. So in the case of word2vec, which is a great algorithm and very useful, but it can't tell the difference between these contexts very well. A transformer, our topic of the day, it also shares this process called encoder-decoder. So let's maybe break those steps down. What the encoder does is it takes in the input representation, so the words you're going to use, and then it goes through a sequence of these encodings where it's just saying, like, let me come up with a numeric representation, and then through a couple of different processes, and then at the end of it, the value is encoded. So I have some numeric representation of that sequence. And then whatever that encoding is, you pass it to the decoder, and you say, okay, here's the way it came out numerically. Now we want you to go back and convert this into text or into some meaning or some output phrase. See if you can reconstruct the information based on the encoded version I gave you. Does that make sense?
I don't know your words do, but do you have an example?
Let's take a sentence like, I need to make a deposit, therefore I'm going to the bank. If you did some sort of like elementary school project where you circle the word bank and you say, okay, which words help you disambiguate this? Deposit's the main word, right? I need to make a deposit, therefore I'm going to the bank.
Yeah, agree.
Therefore doesn't help you very much.
It doesn't make a difference? No, not really.
Yeah, it doesn't inform you in any way. What your brain is doing that's neat is it's kind of highlighting which words are necessary or which things put the current word into context. The encoder part of the transformer is kind of like making up different contexts and finding a bunch of them, different, ones that you and I wouldn't know what they are. They're just like those numbers aren't real interpretable. You get a bunch of these. So you have several different contexts, and then you weight them. Like, oh, this context is very strong. So deposit has, I want to pay a lot of attention to that, put a lot of weight there. And that word is lighting up. You have some representation that says this relates to financial things. Then when you go to decode the information and you encounter that word bank or its representation, it's there with these other hints, these other things you're paying attention to.
So I don't understand. What's the algorithm doing?
It is finding the best encodings and decodings that it can.
Okay, but I feel like your examples are still vague, so I'm still not sure what the computer's doing.
Yeah, it's doing a very technical thing. So I could just spit jargon at you about like, oh, it has a softmax layer, and then it has an encoding step, and then it has a this layer links to this layer. And if people want that technical write-up, there's some excellent blog posts out there they can get into. And they can get the code for this on TensorFlow and go run it and stuff like that. And there's great visuals that explain this, the tensor algebra of this and that kind of stuff. What I think you and I should more talk about is the less practitioner approach and more high level. So like, let's say you were working with some data scientists and they said they wanted to use, or they were going to use a transformer. You could understand a bit about what they're doing and why. The transformer is like a little box that has a bunch of operations inside of it. The first are several steps of encoding. So the encoding is trying to say like, okay, seems to be like an idea here, and it's this sort of attention distribution, saying of all these concepts that are around, these are the ones we're emphasizing in different parts of the sentence. The decoding layer, it gets the benefit of seeing all of the encodings and what previous steps have done. So as the sentence starts to be, let's say it's machine translation, you start to translate some of the first ideas, knowing that you chose to translate fishing as the hobby sport of putting a bait in an ocean rather than fishing like you're trying to scam somebody. That choice, if you will, is present for later parts of the sentence. So when you get to the riverbank, you already know, like, okay, not only am I talking about a riverbank, but I know earlier I was talking about fishing, which bolsters my confidence that this is the correct interpretation of this word a few pieces down.
Yeah, I mean, in theory, it makes sense.
What's amazing is that people figured out a mathematical way to kind of emulate that process. What I described sort of in English of like, oh, you're going to remember this bit and we're already in this context. The magic of the transformer is finding a way to automatically in an unsupervised fashion kind of invent its own way of encoding those contexts and then make them available in the decoding step so that as you process the sentence, there isn't this sort of panicked moment like you get to the word bank and you're like, oh, what do I do with this? You would say like, oh, I have all of these other things in local context, so it becomes obvious to me. Oh, they're talking about fishing and they're talking about water. Of course this is riverbank, because there's so many hints there that the human brain is very adaptive in finding. But machines, historically maybe we tried to write more raw code to get them to do that. Now we're asking them to figure out the process or the mechanism by which to do it on their own.
Well, it sounds like you're considering some interesting problems that the average person doesn't talk about. Or think about, rather. So I'm glad someone's tackling it.
Until next time, then, thanks as always for joining me, Linda.
Thank you.